Hi, my name is Stephen Gensimer. I've been doing some of the measurements of the beam splitter that CSIRO is fabricating for the kagra project. And I wanted to make a little, give you a little description of some of the issues we've been running into when we're doing measurements with these beam splitters at 45-degree angle. So first, let's just think about what happens when we have the beam splitter sitting in the interferometer. So we have a laser inside the interferometer, and the light from the laser comes out in parallel rays, collimated, and it strikes this surface. It's refracted by Snell's law through the bulk of the beam splitter, and then it continues on and hits this reflecting mirror. From the mirror, it turns around and reflects back, and assuming everything is ideal and all these surfaces are precisely flat, then it reflects straight back in the same direction it came once you've aligned this mirror to null the fringes. And from that, you should get the path that is traveled through this beam splitter will change depending on the thickness of the beam splitter, and you should get a phase map which tells you something about the shape of this beam splitter. Okay, so let's think about what some of the problems are. So first of all, let's think about a beam splitter when you're using it in normal incidence. So let's take an optical flat, and it's not going to be precisely flat, but when we do our normal incidence measurements, then we have a laser that comes in here. It passes through the front surface, reflects off the back surface, and then so it comes in, reflects off the back surface, then goes back out the way it came. Okay, and so the total path length through this thing is going to tell us something about how the optical thickness of the beam splitter varies. Now, when the first thing I want to point out is that the flatness of this the angle of incidence here depends on the slope of the beam splitter here. So what I mean by that is, for example, if I have a beam coming in, let's just imagine we draw a normal incidence. Oops. Let's make this normal. Okay, so this is a right angle. Now we have an incident beam at a very small angle compared to that, right? So this will be theta I. And then it refracts through this thing. And this I'm going to call theta. Okay? Now, the path length that it takes through the optic, I will call that P. And let's call the thickness of the optic D. Okay, so how does the path length vary with the incident with the refracted angle? This refracted angle theta, remember this is related to the incident angle by Snell's law. But at any rate, this refracted angle, the relationship is just the simple trigonometric identity. We would say P equals D over cos theta. Now, if the incidence angle is very small, so let's suppose it's much less than 1, then you can say that the path distance here is approximately equal to d. Let's put some numbers on that. So I did a quick calculation. Suppose theta was equal to 10 microradians, okay? Then I calculate that this ratio, the difference in path lengths for P and D, divided by D, so that's the fractional difference in the optical path distance, would be 5 times 10 to the minus 11. It's extremely small, and for an optic 80 millimeters thick, such as the Kagra beam splitter, that would be 0.004 nanometers. Okay, this distance, this difference here, this is P minus D. Okay, so if you come in with a very small change in the angle of incidence here, and when you're in a normal incidence beam splitter, measuring the beam splitter at normal incidence, if you come in with a very small error, small variation in the incidence angle, then you don't have to worry at all about the change in path length due to that incidence angle. Okay. In addition, you can also say that by Snell's law, you don't have to worry about a variation in n in creating a path length difference due to Snell's law. N will only enter in because the optical path length is simply n times p here. Okay. Now, let me clear this quickly and go on. Okay, so let's go on with the beam splitter problem here. Now, suppose we take the beam splitter at a 45-degree angle. The first thing we have to worry about is we have a beam of light coming from an interferometer, and we're going to reflect it backwards with a mirror here. Okay. So the interferometer is going to measure, the first thing we do is we don't put the beam splitter in at all. We just let the beam reflect off the mirror, and we measure the shape of the mirror. Okay, the mirror is not perfectly flat, but we can measure what it is, and then we know. So we can use that for our analysis. Now, when we put the beam splitter in place, this is going to change. Oops, let me make that a little better. Okay, so here's our beam splitter. Now, the light from the beam splitter is not going to go straight through. It's going to be refracted according to Snell's law and follow a different trajectory, right? So that means that we have to move the mirror. We have to move the mirror by this distance, by this much, in order to still use the reference file that we generated with the mirror in place, right? So that's the first thing we did. We compensated for that by sliding the mirror up in this direction by the right amount, we believe, to compensate for that shift. Okay. Then we have to think about the path distance that's traveled by the light going through this beam splitter. So let's again say the thickness of this beam splitter, we're going to call it D. And here's a normal. And we'll say that the angle here, the angle of incidence, I'm going to call that theta. the angle of refraction here is theta. Okay. Okay, so here's the angle of incidence, and then it turns out with the index of refraction, which we have here, which is n, right? For our case, if we go to a 45-degree angle, then theta is going to be about 0.51. Okay. Now it turns out that if we measure the now what we really want to know is, let's say here's the path distance here, p is again the path length, the optical path length that the beam travels as it goes through the interferometer. Okay. Now if there's a little variation of the slope at the front surface here, and that will change the angle of incidence, and that will change this theta, the angle that it's refracted by. Now, if a very small change in theta happens, how does p change? Well, let's just suppose that theta changes by 10 microradians again, okay? Just as we did in the previous example. In that case, there'll be a change in p, which is about 5 times 10 to the minus 11 over p. Sorry, 5 times 10 to the minus 11 times p, which is going to give us a path length change of about 500 nanometers. Okay, so that's a 10 microradian change in the refracted angle here, gives us a path length difference of 500 nanometers, right? Remember, when theta was approximately 0, the same thing, the same tiny error in the angle of incidence gave us 0.004 nanometers. Okay, so this is the huge difference. This is showing us a huge difference between the normal incidence interferometer and the interferometer when we're using it at 45-degree angle. Okay, now that's bad enough, and you can imagine that a very, very small change in n, right? So change in n, or a change in the incidence angle, and by the incidence angle I'm talking about this here, theta I, I'll call that incidence angle. A change in either of those will make this path length change dramatically, right? So that means that we're going to get a different path length here, which is not related to the thickness of the optic, but related to the material, the incidence, to the material inhomogeneity, and to the slope of the surface here, right? It's also going to depend on the slope of the surface out here, and it's also going to depend on the overall thickness of the thing. So it's becoming quickly a much more complicated problem than the normal incidence interferometer. It's going to get even worse, however, when we consider rays. The ray has to reflect off of this mirror and go back into the interferometer. So let's just draw another ray to visualize that. So let's suppose this ray here, we're lucky and the interferometer is aligned so that it travels to the mirror, reflects off the mirror, and goes straight back in the same path and all the way back into the interferometer. Okay? Now let's pick a different beam which strikes at a very slightly different angle of incidence, And so it takes a different path through the interferometer. And when it reemerges here, it may not, if the slope here is different from the slope there, then it may not even come out. This ray may not be parallel to this ray here, right? If these slopes are very slightly different. And so that means that when it strikes this mirror, it's not going to go back in the same direction that it came in. It'll go back in a different path. And when it travels through here, then it's again going to be deflected differently depending on the slope of this surface, and the way it goes back to the interferometer depends on the slope of this surface. So now in order to understand the total path length here, you need to know the slope here, the angle, the index of refraction here, the slope here, the slope of the mirror here, the slope here, the angle incident, the material here, and then the slope finally for this refracted beam. So now I hope you can see that the problem is much more complicated here than it was in the normal incidence case. And in fact, the distance, if you move this mirror to a different place, it's going to change the interferogram again. It's going to change what the interferometer sees. Now, you may notice, now it's true, of course, that all of these things are going to be a problem for the real LIGO interferometer as well, for the kagra interferometer. So all of these effects will still are not just happening in our lab, but they're going to happen in the actual experiment. But we can't simulate what's going to happen in the experiment in our laboratory because the mirror we have here is only a few centimeters away from the beam splitter, right? But in the interferometer, it's going to be several kilometers away from the beam splitter. And so what it actually does to the beam several kilometers away is going to be very different. It's going to depend on the optics that are in the path, and it's going to depend on how far away they are in order to figure out what's going to happen to the return beam, right? So I hope that gives you an idea of some of the additional issues that have been brought up by this 45-degree angle measurement. It's been an interesting exercise, but it seems clear that it'll take some pretty thorough modeling in order to completely understand what exactly is happening when we place the beam at 45 degrees through the optic.